This is Audiommunity, a podcast about our body's never-ending fight with the outside world. Hi, this is Audiommunity, recorded on January 11th, 2016. I'm Kevin Bonham, and with me today are Kate Franz.
Hello.
And Matt Woodruff.
What's going on, everyone?
We mentioned in the last episode, we're actually recording 3 days after the last episode that Matt and I recorded.
Which is
we decided,
super first.
Yeah.
Yep.
Although we should really wait until they actually get posted online, because it's entirely possible that 6 months will go by and they'll just languish on my hard drive. But we decided that we wanted to record again with Kate because last time Kate had to cancel last minute
Yes.
because her mouth exploded, apparently.
Yes, it did. I was bleeding from my mouth. I had an abscess, a very infected tooth, and I thought I just had a cracked filling, and my dentist was like, oh, no. You need a root canal. To which I was like, no, I think it's just a cracked filling. So then she proceeded to hit me in the tooth and say, did that hurt? And I screamed, and she said, nope, you're getting a root canal. And she put me on antibiotics immediately. And I've just been sitting here feeling sorry for myself for the past 3 days.
That sounds awful.
I can't get in to actually get it done until tomorrow. So by the time anyone hears this, I will have experienced my first and hopefully last root canal. And I will have been a big person about it and did not cry. In case anyone was counting, did not cry.
How many painkillers are you getting? Or how much painkiller are you getting?
She didn't even give me nice painkiller. She gave me ibuprofen. So
That's
when I get
terrible.
this new dentist to do like the root canal, I'm going to ask for like at least like a Vicodin. Come on.
You're like, damn it, I need the opioid, okay?
Yeah, come on.
Can
So
you
I don't
just
know.
ask for house? Just,
For
like,
house.
ask,
I would
ask
like
for
the house
Dr.
treatment.
House.
Yeah. That would be 18 Percocets? Thanks.
Yep. So
Although we probably shouldn't joke about drug dependency. Instead...
Speaking of, what are you drinking, Kate?
Water. Just warm water. My diet has slowly been restricted as my tooth has hurt more. So I started with like soup blended with rice and oatmeal. And then this morning I couldn't eat the oatmeal. So today I just drank gross smoothies where I put things in that sounded nutritious, like peanut butter for fat and kale for green things. And
Did you really do a peanut butter kale smoothie?
I made a kefir peanut butter kale banana smoothie with a little bit of cayenne. Because you put that much berry and banana together, you gotta stop yourself up. So you need the cayenne to keep it moving through. Yeah.
I think the kale does that, does it not?
Oh, for the love of God.
Yeah.
Wow.
Well, I mean,
all
like,
right, so can we post the recipe
nutrition.
for that?
Gotta push it out.
Yeah, I think you should write up a recipe like a food blog, and we should post that along with this episode. That is gross. So I am drinking, this time, I'm back to the Snow Wit white IPA from Sierra Nevada. I am just rating the refrigerator, and it doesn't seem to be going down in the time in between
Oh, that's
the
good.
episodes, so I figure I might as well just drink it until it's gone.
Right, the beer elves keep restocking.
Well, not restocking, but no one else is depleting.
Oh,
so
okay.
pretty soon I'm going to be down to only chocolate stout, and then I might have to go to the liquor store and get some for myself. But
Okay.
until then, I've
Yep.
got a few more IPAs in the can.
I've been playing with this idea of doing a dry January. It's thus far just been fortunately enforced on me because I'm on antibiotics, not really drinking. I hadn't had any alcohol before I had my tooth injury. So I don't know. I'm feeling pretty good.
Yeah?
I think it's the kale cayenne smoothie with peanut butter.
I don't know, but maybe save one of those stouts for February 1st.
Okay, will do. Do we have are we recording an episode on February 1st? We should.
Kate
Matt,
hasn't
what are you
had
drinking
any alcohol
this
for
evening?
30 days. Now she's sloshed.
Yeah, so I decided to just throw in the towel, and I'm drinking straight vodka for this episode. Yep. So came home.
Why?
Emily wanted a kangaroo, which, for those of you that don't know, kangaroo
Like me.
is what you call a martini, except it has vodka, but that's a different drink. That's an actual martini. Vodka martini, actually a kangaroo. There you go. So I'm drinking a kangaroo. It's
That
got
doesn't...
dry vermouth in it, and it's got an olive. So, yep, drinking vodka.
That just seems like a bad idea all around.
Yep,
but
we'll see how it goes.
Doesn't matter. So
You know what? Let's have a hard liquor episode where I drink tequila and everyone else drinks whiskey or vodka.
Right. I mean, I do usually drink scotch. It's not like vodka is a huge shift towards the alcoholic direction, right?
Scotch is like dignified. Vodka to me is like, spring break!
well, I guess if you're drinking a martini, although, you could drink vodka on the rocks if you were Russian.
Right.
But I don't know.
Or just an alcoholic.
Or just an alcoholic. Yeah, sure. None of us are alcoholics, as far as I can tell. So if this triggers you, I apologize.
I apologize for not ever again apologizing for a trigger. I'm sorry. I'm not going to do that.
I was actually just thinking, Kevin is apologizing and giving a trigger warning?
But I was doing it ironically.
What?
Facetiously.
Nope.
Yeah.
I object both to the actual and ironic
Does my trigger
use
warning
of
trigger
triggers.
you, Matt? Is that what you're saying?
It does.
Oh man.
It does. I'm feeling triggered.
Yeah.
All right. Well, let's trigger you with some other stuff. I am going to poorly introduce the concept of lymphatic vessels because. So we're discussing a paper today that was published about 6 months ago in Nature, and it's super cool and pretty straightforward. But it requires a fair amount of introduction, like more introduction than I think we typically give, because the end results of this paper are pretty much like, hey, we found more lymphatics. But the paper is called Structural and Functional Features of Central Nervous System Lymphatic Vessels. And as you might imagine, what this paper shows is that we actually have lymphatics in the brain. And this was kind of a novel finding. It's kind of, I don't know if surprising is the right word. I think over the last couple of years, it's sort of become obvious that this should happen. But basically, for a long time, we didn't really know how the immune system was involved in the brain. And we've talked about this on episodes before. For a long time, people just thought that the brain didn't have an immune system. It was immune privileged. And for a long time, what we've thought immune privileged means is no immune system. And of course, over the past decade or so, we've started to see more and more examples of ways that the immune system is involved in the brain in pathologies like multiple sclerosis, during brain infections. I think we've talked about before, there's a medication called Tysabri that blocks T cells from getting into the brain. And one of the side effects of that is an increased prevalence in a certain brain infection of a virus, JC virus, that doesn't happen in normal people. So it suggests that there is immune surveillance of the brain. I don't know. Go ahead.
Sorry, I'm going to jump in. And I think we've mentioned before that the immune system is a part of the normal function and development of the brain as well. So as your brain is developing and you're extending neuronal attachments, you're creating neuronal networks, and eventually at age 2, 3, 4, those neural networks become sort of streamlined and trimmed. It turns out that the way that your neurons are trimmed so that only the correct networks remain is through components of the immune system. The complement components are really critical for that pruning process as well.
Right. And also the brain macrophages too, right? The
glial cells.
The glial cells? Yeah. Oh, I should mention also, this is like Matt's major area of study, or at least it was in his graduate work.
Not the brain.
Yeah, right, the lymphatics. And so I decided that I should probably introduce this instead of Matt, because if Matt introduced it, I would have nothing to contribute. And I don't know, Kate's just going to sit there in pain with her tooth.
I'm gonna ask questions.
Okay.
The first being lymphatic vessels. Interesting.
Yeah.
How is this related to something that I know,
on.
like the lymph node? I've heard of lymph nodes. Lymphatic vessels maybe less so.
Right. So the lymphatic system, well, let me back up for a sec. I think for most people, or at least most people that I know, their interaction with their lymph nodes, with the lymphatic system, is through the lymph nodes, which they know sometimes get swollen during infections. So if you've had an upper respiratory tract infection and you've felt like in your neck there's some swollen, people often call them glands, which is not technically
Please
true, but
don't
they say
call them glands.
Swollen glands in your neck. Those are actually lymph nodes.
Or your tonsils.
Tonsils they're not actually lymph nodes, but they are a lymphatic structure, absolutely.
Really?
Or,
I thought they were lymph nodes. This is all.
Am I wrong, Matt?
I believe
I'm pretty sure
that
the tonsils
they're
are
slightly different. They're packed with B cells regardless. I mean, they're definitely lymphatic lymphocyte-containing
tissues.
Structures, and I believe they're considered secondary lymphoid organs, but I think that the structure may be a little bit different.
Yeah,
Interesting.
So broadly speaking, we say that the lymphoid structures are basically organizing centers of the immune system where immune responses tend to happen. So you have lymph nodes littered throughout your body. If you can Google pictures of the lymphatic system and you'll see like these little, they look like beads on a string. The beads are the lymph nodes and the string is the lymphatic vessels, and they're shot throughout your body, kind of like a parallel circulatory system. But in addition to lymph nodes, we have other what are called secondary lymphoid tissue. So the tonsils are one example of this. We also have in the gut, there are secondary lymphoid tissues called Peyer's patches that are just organized structures of stromal cells and immune cells.
Yeah, those are basically lymph nodes.
Right.
All intents and purposes, they're essentially just lymph nodes on your intestinal wall.
Right. And then, so we say secondary as opposed to primary lymphoid structures, which are places where the cells develop. So B cells and T cells go through their primary development. They become mature naive cells in the bone marrow or for B cells and in the thymus for T cells. And so secondary lymphoid tissues are basically where after you have a mature cell, they get activated. So most of the time, your T cell isn't going to get activated out in the periphery at the location of infection. Actually, it's going to get activated in one of these secondary lymphoid structures. And that's sort of the point of the lymphatic vessels. That's the point that the immune system has sort of co-opted the lymphatic system to do. I don't think that made sense as a sentence. But whatever, moving on. So basically, the idea of the overall point of the lymphatic system, and I'm paraphrasing Matt here when I say this, is as blood is circulating throughout your body, your blood vessels are not an entirely closed system. Some amount of fluid actually can leak out into your tissues.
And should, right? I think that's important. And, so you have a lot of nutrient transport, obviously, that has to come out of the blood. You have a lot of oxygenation that needs to be transported. Not every cell has direct contact with the lumen of a capillary, right? So there's a lot of things that need to come from your blood that need to touch every cell in your body that aren't just blood vessels. And so how do you actually get that transport? And one of the ways that you get that transport is sort of the slow leakage of blood volume out of blood vessels into the interstitial fluid. And this is fluid that sort of just bathes all of the tissue in your body, and it just allows each individual cell in your body to sort of operate at homeostatic levels.
Right. And so one of the things that you need to do as this blood volume is leaking out into your tissues is you need some way of that liquid getting back into your blood. And it's not going to go in the same direction. Your blood vessels are under extremely high pressure, and so stuff is going to come out of it, but it's not going to go back just by sort of diffusing back into the blood vessels directly. And so instead, we have this series of tubes, like the internet, that collect...
Thanks, Al Gore.
Yeah.
Oh, no, who was that? That was not Al Gore. He invented the internet.
Right. No, we've definitely made this joke on this podcast before because I think it's hysterical. But anyway, the lymphatic vessels collect the fluid that gets out into your tissues and collects it back and eventually deposits it into a central duct called the thoracic duct that's sort of in your chest, I think sort of behind the heart. Is that right?
It runs up back behind it. You can sort of think about it as running up your spine. So starting in your abdominal cavity, your upper abdominal cavity, it sort of runs up along your spine, back up, and then, as you're about to mention, dumps back into the circulatory system.
Yeah, and as I say it dumps back, it occurs to me that I have never actually asked, how does it get from the thoracic duct back into the blood? Because I just mentioned your circulatory system is under extremely high pressure. So how does the lymphatic fluid actually get back into the circulatory system via the thoracic duct? I have never considered that before. I've always sort of just imagined it as like an open tube that sort of dumps like a waterfall, and clearly that is not physiologically possible. So
Yeah, I don't believe that is how it works. No, so I think you mentioned that this is going to be unidirectional flow, right? So you've got flow out of the blood vessels and into the lymphatic vessels. And those lymphatic vessels at the very beginning of their journey, sort of imagine a kind of capillary, but a blunt-ended capillary, so it's not really connected to anything. And those capillaries all have pores in them. You can imagine like little one-way valve flaps where extra fluid sort of fills the capillary, but it can't escape back out into the tissue. And so all along the vessel, as these vessels sort of centralize, if you spread out the fingers of your hand, you can imagine all of these capillaries extending all the way down each finger, but you really may only have one lymphatic vessel running from your hand to your elbow, right? So all those smaller vessels have to kind of come together. And so what you're getting is you're getting unidirectional flow through the this network of capillaries that all have unidirectional valves. So as fluid flows up towards your elbow from your fingertips, those valves are going to keep backflow from occurring. And the same is true, I believe, all the way up through the thoracic duct. As far as the actual emptying of the thoracic duct into, I think it's the right subclavian vein, that's where it's going to end up entering back into the circulatory system. I assume that there's just a unidirectional valve at that site. I also expect that because of the pressure in your chest, I imagine there's a lot more musculature moving.
Yeah, and I wonder if the pressure is building throughout that network. So at the terminus of all of those lymphatic vessels, where they're picking up the fluid, pressure is very, very low. But as it sort of centralizes, you've maybe got the sum of a bunch of different pressures coming together. So maybe the pressure at that site, at the subclavian vein, is just higher than typical in the lymphatic system, and your veins are going to have much lower pressure than the arteries in your blood. So maybe it's sufficient.
And it's worth pointing out how this fluid flows generally. So there is some indication that there is some smooth muscle action that occurs as far as sort of pushing fluid along. But for anyone that's ever been on an airplane and noticed that your ankles swell up, the reason for that is a lot of the fluid transport through your lymphatic system is dependent on actual active musculoskeletal movement. So you moving your legs around tightens and relaxes those muscles. And when your muscles tighten and relaxin is not a word. When your muscles tighten and relax, that sort of pumping action that's created is one of the major driving forces of pushing the fluid along those unidirectional systems. So as you just mentioned, there's going to be, temporary moments of high pressure along these vessels. And I do wonder if it could accumulate towards a more central high pressure. But also I wonder how things like heart pumping and how things like your lungs inflating and deflating, I wonder if those things also put pressure on that central duct.
Yeah, unfortunately, none of us are fluid physicists, so we can't actually describe this with any greater detail than sort of high pressure, I think.
Yeah, I pretended to be on a paper actually recently. It's a terrible paper. I apologize for anyone that reads it.
So all the fluid goes from like your extremities and flows towards your heart, right?
Yes.
Correct.
So is that why you're not supposed to get a massage where you massage away from the heart? You're always supposed to massage towards the heart so you don't pop all your lymphatic vessels?
That's a really good question. I have no idea.
I do not know the answer to that. I
do know that in hospitals, one of the things that nurses have to do for patients that are bedridden is they basically have to massage their extremities because they can't do all of that skeletal muscle movement that's going to pump their lymphatics. And so if they don't get massaged, basically the lymph will pool in their extremities, in their feet and in their hands, and that's
absolutely true.
No good.
Yeah. So that is what those massages are for. As far as massaging away from the heart, I'm not quite sure.
I think that it would be very, very difficult to pop your lymphatics through massage.
Well, I was being a little facetious.
Yeah,
I suspect, but who knows? Maybe I'm wrong. Maybe massage therapists out there are listening and saying, "Yeah, I totally did that once." If so, write in, let us know.
It does sound horrible.
So
I also just wanted to comment that the person who said the internet is a series of tubes was the Republican senator from Alaska, Ted Stevens.
Oh, fantastic.
I forgot about Ted Stevens.
Thanks, Ted Stevens.
I'm so glad I remember that he exists.
I have a friend who lives in Alaska now, and she loves everything about it except for the politics, which is interesting. Anyway, I may cut that out. So, because it just is apropos of nothing, and it has no value whatsoever.
I mean, I felt like you were going to decide whether or not you were going to come down one way or the other. Then you decided not to. And then, here we are.
Anyway, so we describe all of this stuff about the lymphatics because really the lymphatics are actually kind of tough to study. So, when you study biology in high school, you probably see a picture of the circulatory system. You know that you have blood because if you get a cut, you see the blood. And it seems pretty obvious that that's something different. And, the circulatory system is a closed system. It has this pump that's the heart that is fairly obvious that if that gets damaged, you die. And I feel like the lymphatics are sort of this sort of unremarked on and unconsidered organ system or tissue system because it's not super obvious that it exists. It's there and it does all this work. But we don't think about it much. But the reason that we think about it on this podcast and that we're going to talk about it today is because as all of that fluid is coming out of your tissue, in addition to just carrying the fluid back to the blood, you are also going to be carrying any pathogen, any bits of pathogens, any signaling molecules present in tissues that are undergoing an immune response. And so this actually makes the lymphatic system a really great network for surveillance for infectious disease. And actually, that's the point of these secondary lymphoid structures that we talked about, the lymph nodes specifically. They are spaced along the lymphatic vessels at intervals, and they collect all of the upstream lymphatic fluid, as well as any pathogens, any bits of pathogen, and any signaling molecules, as well as dendritic cells that actually specifically migrate from tissues to the lymphatic system in order to deliver antigens to T cells and B cells, essentially, and get immune responses going. So these are critical for having an immune response generated at a tissue site. So a T cell doesn't have to surveil every square inch of tissue in your body. All it has to do is surveil all of the lymph nodes and other secondary lymphoid organs in order to look for the presence of pathogens that are going to drain into those secondary lymphoid structures.
Right. So maybe it's good to go back to the visual then. So if you extend your hand out again, extend your fingers, right? Let's say you have a cut on your thumb, you get a minor infection, right? You've got dendritic cells at the site. We've talked about dendritic cells in the skin. Those dendritic cells at the site of the cut on your thumb are going to become activated, and they're going to use that lymphatic system to find their way to the closest downstream lymph node, right? So you've got dendritic cells that are going to sort of migrate along your thumb towards your wrist. And when you hit your wrist, right, you've now got lymphatics draining from all 5 of your fingers. And so those lymphatics are going to continue to collect all the way up your arm. And one of the major lymph nodes that people look for infections in small children is the armpit lymph nodes, right? I'm sure you've had your doctor test under your arm, and what they're looking to see is if those armpit lymph nodes are inflamed. So a T cell, rather than having to go up individually along your circulatory system and check each one of your fingers for an infection, can now just go to your armpit, hang out in your lymph node for a while, and if it happens to see a dendritic cell come by that has something from an upstream site, then the T cell knows, oh, there's an infection out there, I need to respond. And, a series of homing mechanisms will eventually find that T cell to the infection site, so it doesn't have to quite worry about that yet. But it's just a really good way, as Kevin just mentioned, of surveilling a large area while not having to waste a lot of time looking at every square inch.
Exactly. So it's sort of like you have your dendritic cells, your scouts out on the periphery. So if we switch up, actually, I don't think we've used a metaphor yet. If we have a sort of like army metaphor, you can imagine that you don't want to try to send soldiers, you don't want to try to defend with your soldiers every single square inch of territory. You've got, forward operating bases. You've got scouts that are going to go and surveil different locations, and then they're going to report back to the base and, bring along signals and say like where the thing is located, what the nature of the threat is, and then at that central base, then they can sort of devise the plan and send out a concentrated force to the correct location. And this is sort of analogous to what the immune system is doing. We have these, the lymph nodes are sort of these forward operating bases. We have the scouts that are the dendritic cells in the tissue, and they are going to bring back information about infections that are occurring to mobilize a response that is then going to travel to the site of infection.
Right. And so this is my own little plug, and this is something that I've taught lymphatics to a couple of different classes before, and my own little shtick here, and take it with a grain of salt, maybe, although I'm pretty sure that I'm right in this. I think most immunologists like to think about the lymphatics and the lymph nodes in particular, as extensions or manifestations of just the immune system. And I think that that's not entirely appropriate. I think we just talked about all of the lost blood volume and things like this. I would think of the lymphatics first and foremost as a recycling system. So you're basically losing all this fluid and you're trying to recycle it back into blood volume so that it can be useful again to you, so you just don't lose it as an organism. But in the process of recycling, as Kevin mentioned before, it's not just that the lymphatic system is going to be carrying immune cells. It's also going to be carrying anything from the infectious environment, including infectious particles. So if the primary job is recycling, but some of these bacteria at an infection site get carried off in the lymphatics, and eventually that recycling system pumps everything back into the blood, if you have no way of filtering out that infectious material before it gets to the blood, all of a sudden you've taken a localized infection and you've turned it into a systemic problem. And so I always argue that the immune component of the lymph nodes is a really good co-opting of this recycling system, but that the first and primary role of a lot of these lymph node environments is to make sure that any lymph that's coming through the system to be recycled is clean of infectious particles before it gets pumped back into the blood, because that is an immediate and extraordinarily serious problem.
So maybe we can extend my analogy a little bit and say, rather than this is a central province of the army, this is a municipal waste stream that is looking for the terrorists that are trying to poison the water supply. And if they see poison, then they know that somewhere upstream from that recycling center, there's some bad guys operating. Does that...
I'm for that.
Okay.
Sure. Yeah,
okay with
I like
that analogy?
I like that. We'll develop it more.
Okay, sounds good. You should make a comic about it.
All right.
So this is the lymphatic system, and immunologists sort of often get like one lecture on the lymphatic system as like, hey, study lymph nodes. These are the things that you extract from mice if you want to find a bunch of T cells, along with the spleen. I guess if you're super lazy, you just go for the spleen.
Yeah.
If you are a little bit more ambitious,
you're not doing it right, by the way. You're not doing it right if you're just pulling the spleen.
Because the spleen is also a secondary lymphoid structure that's essentially a giant repository of T cells and B cells that are surveilling the blood. Because it turns out that infections in your blood are a real bad idea. So
which means that if you're studying a localized skin phenomenon and you're pulling the spleen, it means all of your primary responses were actually going in lymph nodes, and all you've seen is stuff that has recentralized or has leaked out into the blood. So you've missed probably your entire phenomenon. That bugs the hell out of me. I'm sorry.
Yeah, you should be sorry, Matt. You're terrible for wanting rigor in your science.
Right.
How dare you? Okay, so that's sort of brief crash course on the lymphatic system. It probably gets much less attention than it deserves. But the paper that I mentioned up at the top, and I didn't mention the authors. So this is in Nature, Structural and Functional Features of Central Nervous System Lymphatic Vessels. The first author is Antoine Louveau, and the last author is Jonathan Kipnis.
Nice job with Louveau.
Thank you. I did take 2 years of French in high school, so I can say s'il vous plaît and
le veau.
And le veau.
Those are the two things I learned.
Yeah. No, I learned how to say, so in French class, you learn to say, I don't know, is je ne sais pas. But it turns out that in France, of course, nobody says that. That'd be like saying, I do not know. They actually say, je sais pas. So that's the other thing I learned.
Okay.
Cool French.
Well,
cool French lessons.
Yeah.
Assume useful. Yep.
Anyway, I'm going to cut that too.
No, I liked that. It was a nice interjection.
All right. So the point of this paper is essentially, hey, we looked in the brain. We know the immune system should be in the brain. So we think that lymphatics should be in the brain. And hey, we found lymphatics in the brain, which,
Sounds very obvious.
Doesn't it?
I mean, yeah, but also apparently no one had looked until July of 2015. So.
Yeah, isn't that weird? Is this true?
Yeah.
Matt? Has no one looked?
It's weird that this has not been done before. This is one of those things that... So, Kevin, you mentioned earlier that the lymphatics are difficult to study, and that is sometimes true. Here's a really easy thing that you can do with lymphatics. You can inject a dye. It's like pen ink called Evans Blue, and you can inject it anywhere on the body. And what happens is, because your lymphatic system is a recycling system, the Evans Blue is in the interstitial fluid initially, and then it goes into the initial vessels, and it goes into collectors, and it goes into lymph nodes. And so basically what you can do is you can track the entire line of lymphatic flow from the place you injected to the eventual lymph node, and eventually throughout the entire body of the animal.
But wouldn't you eventually get it into the blood?
Yeah, eventually it does go into the blood. Eventually it goes everywhere. So you have to be a little bit quick with your Evans Blue. But if anyone wants to take a look at this paper, and we're going to talk about it in just a second, I think, figure by figure, but figure 3 is literally an Evans Blue injection into the brain where they just looked to see if there were lymph nodes that lit up. And that is one of the easiest visual histological experiments you could ever do as an immunologist. So
yeah, I'm looking at it now. I'm
I think
like, okay,
this
looks legit.
Yeah, right?
Looks like a
you
brain,
just see...
and there's a weird blue nodule. Okay. Lymph node.
No, exactly. So it's just blue, right? That's the readout. Yep, lymph nodes are blue. So I think that this is one of those weird examples where there's just a dogma that surrounds this sort of thing. And so no one ever...
wanted to waste the money,
I suppose, or ever really just spent the time to do the experiment, because everyone just assumed that there were not lymphatics in the brain,
right?
Because that's what everyone said.
Let's just back up and for a second say, like, okay, so we have to remember that for a long time there's this dogma that there's the blood-brain barrier and there is no immune response in the brain, right? So that's dogma for a while. So, of course, if there's no immune response in the brain, why would you assume there's lymphatics in the brain? Other than the fact that there's like 1 billion friggin' capillaries and your brain is like one of the largest suppliers of oxygen, no lymphatic fluid is going to leak out. Come on. But anyway, who cares?
Right. And how's your brain getting, again, nutrient transfer?
Yeah.
Right.
So let's just ignore that for a moment.
This is basic physiology, right?
Let's just ignore that and say, okay, so we're going to take what Matt mentioned as the sort of received wisdom that the lymphatics are just for the immune response, and there's no immune response in the brain, therefore there shouldn't be lymphatics in the brain.
Right.
Now, over the past decade, as I mentioned, more and more evidence that actually the immune system is a really important part of brain physiology. There's a lot going on up there. And
I think you're being generous when you say decade.
Okay, fine. What,
30 years? When's the first time MS was discovered to be an immune phenomenon?
Well, but you could say like that's a pathological condition and normally the immune system isn't in the brain.
Okay, so let's go with that.
You could make that argument.
Let's go with that. So it's a pathological condition, right? So let's say that is a breach. You discover that that's a breach 30 years ago, right? What happens with inflammation? With inflammation, you get infiltration of immune cells into whatever site, right? And the reason that you get inflammation is because you get dialysis of the blood vessels. and you get the expression of adhesion molecules and all of these things that the immune system uses in order to integrate into a tissue.
Yeah, but Matt, you're assuming that the people who are studying this actually have a holistic view of the immune system.
I know, that's why I'm moaning right now and bitching.
Ouch.
So getting back to my point, so I feel like once that changeover started to occur, once more and more evidence started to accumulate that actually there is an immune response in the brain, once that happens, once you make that assumption, the assumption that there are lymphatics in the brain sort of comes right along with that. I can tell you that I never once questioned whether there were lymphatics in the brain. It never even occurred to me as a question to ask. Because of course, if there's an immune response in the brain, there's got to be lymphatics there. So
Right.
I would never look up, I would have never gone to PubMed and been like, what's the paper that first showed lymphatics in the brain? Like, why would you do that?
Yeah, I know, and I was actually, it's funny that you say that because I would have said the same thing. I think until the end of my PhD just assumed that there was some sort of known fluid outlet for the brain because of what I know about how the immune system works, but that's not always enough. People don't always prove those things. And so I'm really glad that this group went through and actually fundamentally like proved this thing, but I agree with you. I just sort of assumed always.
Right. And so that's something that happens really often in science where there's, you know, either a dogma against a thing, which I think is why no one looked for lymphatics for, you know, say like before the year 2000. And then the reason no one looked after the year 2000 until this group is because once you realize there's an immune system in the brain, you just assume that there's lymphatics there. But
I can't believe that like no grad student like shot up their mouse with this what is this dye called again?
Evans Blue.
Evans Blue, and let it go just a little bit too long and was like, F. Okay, you know what? I'm just gonna open this puppy up and see what I see, and didn't think and like.
Can I tell you, doing sections of the brain? Yeah, I was gonna say, getting into the brain is actually like, really, really hard. I mean, not really hard.
So this isn't even sections of the brain.
Yeah, I was saying,
this isn't sections of the brain.
Up the brain.
No,
like,
it's actually the throat. They're actually looking at the throat in that picture.
Yeah.
The picture on the right, H.
Okay.
That glossy thing running vertically, that's the trachea.
See? Look at this.
Right, but that's not actually, this is looking at these what am I looking at here? But that doesn't show that it's in the brain though, right?
No, it shows that it's draining from the brain because they did the injection in the brain and then they see these deep cervical nodes turn blue.
Yeah, if you saw this upon, I guess.
Just by when you did an IV injection of Evans Blue, like you wouldn't necessarily assume that this was draining from the brain, right?
You wouldn't know, but the bigger
you gotta
question
look for
that comes. Oh, sure. The bigger question in my mind is how many people did that experiment and were like, oh, the brain drains to the cervical nodes and then didn't turn it into a Nature paper. I'll bet you there are 50 scientists out there that looked at this paper and were like, ah, damn it.
That's fair.
Anyway,
we should also mention that there's.
I think that's the best sort of paper to publish.
Oh, it's a great paper.
Because people
it's perfect.
They don't question it. They know that it's true, and they just feel like upset that they didn't have the idea to like finish it all off before.
Yeah, and we should say that this is not a paper where the authors were like, oh, I saw Evans Blue drained from the brain, publish a Nature paper. Like, they actually did a fair amount of work here. So the figures before figure 3 are staining for all of the surface markers of lymphatic vessels, looking at signatures of the immune response. So in figure 1, they're looking at Live1 and CD31, which are signatures of lymphoid stroma. Am I getting that right?
So, yeah, CD31 is going to be general vasculature. Live1 is going to be your lymphatic specific marker.
Right. And they also look at, later on, they look at podoplanin.
Yeah, so they do podoplanin, which they'll be positive for. They've also got the prox mice, which are a transgenic line that are going to... It's basically a red fluorescence protein that's driven by the expression of what's considered a lymphatic specific promoter. Although I'm not super happy with that mouse, but for the purposes of this paper, it's perfectly fine.
It's not
but
their
anyway,
only bit of evidence. It's like another piece of evidence.
They do a perfectly fine job of showing that they can stain for lymphatic vessels in the brain, which, is novel because it's in the brain. But other than that, I mean, the ability to do this sort of work has been around for 20 years. So it's good. I mean, it's well defended. It's fine. No one is going to argue that these are not lymphatic vessels in the brain.
Right.
They're definitely that.
Yeah, absolutely. They do a really rigorous job of demonstrating that it's there.
Yep.
I didn't read through all of their discussion of what this means. But I suspect because it's in nature, they do a good job of defending that this is important. And it is. I mean, I think it's...
Well, they've got all the normal things. They've got T cells in the lymphatic vessels. We know that T cells go in lymphatic vessels, right? I mean, it's, but I feel like we should actually know the things that we think we know. We absolutely should.
And this is really important because this shows that the things that we thought we knew, that the things that I assumed when I was in graduate school about lymphatics in the brain, turns out those things are actually true. And I think it's important that occasionally we step back and say like, oh, yeah, there's a lot of shit that we just think we know and we don't actually have it demonstrated. Because the problem on the other side of this is, imagine they looked in the brain and didn't find lymphatic vessels, right? That would be really interesting. And that would have been really useful information to have. And I would have never thought to look.
Yeah, I mean...
The cases where this is really important is where the things that we think we know are actually not true. And the person that goes to look for it doesn't find it. And then that leads into like whole new research areas. And I think that's really important.
So I think that there's some retrospective thinking in the argument that we're putting forward here, because I have spoken with people that talk about immunology of the brain. And I don't think that everyone made the assumption that there were lymphatics in the brain. I think that there were people that believed that somehow things that got into the brain were just broken down by unspecified manner, and that I don't know how they ever dealt with the liquid problem.
Well, that's just lazy thinking.
I was trying to... Right, sure, maybe.
Do you think that they didn't... if you had asked them if there were lymphatics in the brain, they would have said no? Or do you think that they just never thought about it? Because those are two different things. I think they would have said no. Really?
I think they would have said no. And then I think that I would have pressed them, and I have actually had this conversation. I think I pressed for the liquid, right? So the physical things, you can understand that a T cell could go into the brain and be active and kill a bunch of stuff and then die, right? And we know that glial cells pick up cell debris. That wouldn't be so much of a problem. All of the cell debris, all of the stuff, that could all be recycled and broken down and all those things. The question of edema was more problematic for people, right? Because when you open up those blood vessels so that immune cells can get through and you get dilation and leakage, you get a lot of fluid volume. And as you mentioned before, your vascular system is pressurized. So how does that fluid actually get back into the vessels, right? And I think that was the problem that people had. So,
well, I could give an argument for that. I mean, it's clearly false argument, but you could say, well,
sure,
T cells, in order to get out into the tissue, they don't actually need to carry fluid with them. They have this process that I think we talked about on a very early episode, where they basically roll along the wall and then they stop and then they squeeze themselves through the vessel wall.
But we know that in every other place in the body, when they do that, they bring fluid with them.
Sure.
Right? So you can make the argument that in the brain, that's the only place where no fluid escapes. Well, the brain is unique
in a lot of different ways. So, like, okay, I could imagine someone making that argument. But the point is that if you're going to make that argument, you should do the science. You should actually do the experiment and see if you're right, rather than just assume. And that's what I think is so cool about this paper, is that it's like, you go looking for a thing like this that no one's ever looked for before. And even though you show something that I think Kate said it earlier, like, it seems fairly obvious. Like, it's surprising that no one had done it, but you do it and you get a Nature paper, which is rad. And I also think that had they not found lymphatics, if they were thinking about it correctly, as you mentioned, like, what the heck is happening with all the fluid? How is the immune system operating there? that could have led to a really interesting, probably longer project. Whatever grad student was on that project would probably be hitting
here's what I think
themselves
would
over
have
the head.
actually happened. Yep, we didn't find lymphatics. All
New
right,
project.
well, I guess on to project 2.
Right. But I think that the person that followed up that observation would have had also a really awesome paper, would have been a lot more work. And I think that it's important for scientists to be thinking about answers that they think they know that don't actually have a solid basis.
Yeah, and I think that they're built into that is this thing that I hear it from grad students most often, I think, although I hear it from postdocs as well. And that's that, you know, back in the day, science was so much easier. No one had discovered anything. You know, all of the observations were easy observations. And at some level, it's totally true. I mean, if you ask your PI how long their postdoc was, it's significantly less long and significantly shorter than you will likely spend on your postdoc if you become a PI, right? Like, people moved through science a lot faster. Nature papers, science papers were much more straightforward. There were a couple panels each. You know, the game has changed, but the problem is not so much that everything has been done. The problem is this assumption that everybody has always thought about things correctly, and that everything that you've been taught about the immune system or any system is exactly the way in reality that it was taught, right? There's tons of things that change the fundamental way that you look at these systems. And if you assume that everything works exactly the way that you were taught, and you have no literature to back that up, then chances are good that you're missing something really basic and really obvious. And we're still in that phase of science where these really basic ideas get revised all the time. So anyway, I don't like people telling me that there's nothing basic to be discovered in science, and then having brain lymphatics be published in Nature in 2015.
I agree with you completely. I think a lot of people, especially as grad students, get a little jaded, feeling like there's nothing new to discover. And I mean, this paper very clearly, but I mean, so like you have like, to go like more philosophical science on this, like you have the rules, but like you really get to like kick the tires on a lot of these like assumptions that you have, and you can find really interesting things if you just like don't adhere to the dogma and kind of tool around with these things. But
or even just get away from the topics that people have beaten to death. Chances are good as a grad student, you are not going to discover something super fundamental and undiscovered about a Treg at this point. It's likely not going to happen. And I'm sorry for Treg biologists. I'm sure that you will contribute extremely well to a really important field, but you're not going to rediscover Tregs.
Have you guys read The Structure of Scientific Revolution by Kuhn?
Yeah. It's pretty good.
So this is a really important book, and I have some quibbles with it, but I think it's really important for scientists to read. And the idea behind this book is that you have revolutionary science and you have what he calls normal science. And normal science is sort of the process of iterative experiments about stuff that we know a lot about. There's specific rules, and we're just sort of like getting into the details. And then there's revolutionary science, which is sort of the things that push at the boundaries. And he's talking about like really fundamental shifts in understanding. But I think that you could apply that on a smaller scale to the biology of subfields. So there's dogma, and there's sort of like, okay, we know that there are transcription factors important for Tregs. Or you discover a new cell type, you say, okay, there's probably transcription factors that are involved in that cell type. Let's go find what it is. And that's not super revolutionary. It's interesting, it's useful work, but it's not revolutionary.
It's like you look at the paradigm of the science, and you can make a hypothesis, and the paradigm will predict the answer. And when the paradigm predicts the answer, that's normal science. And then when you have like revolutionary science, you completely shift the paradigm. There's no way to make the hypothesis. There's no way to predict what's going to happen. It's like you can't make. So it's like the theory of evolution is like a paradigm of like,
or like the central dogma in molecular biology.
Yeah.
But what I'm saying is that I don't think all of the paradigms are that high level of paradigm. I think that like the immune system isn't in the brain. That's a paradigm that existed for a while.
Right.
and then it was overturned. And that's a kind of revolution. I mean, it's not as big as like if I proved that the central dogma was not right, but
no, but it's pretty big.
But it's important,
right? It's pretty fundamental.
Yeah.
Like that's what we think with, and it turns out that it's a problem when your immune system is all up in it, right? Like
yes.
It's I don't know. It's yeah. Let's just leave it there.
Okay. Okay,
Rather
so we
than
can leave it there
pontificating
with
all about
that.
science.
This has been Audiommunity, and we're not using episode numbers anymore because probably this is going to be episode 17, but we're going to try to move away from that and record more often, and then maybe roll these things out, not necessarily in the order that we recorded them. But you can find us at emmunity.org, emmunity.org. If you want to subscribe to the show, we're in iTunes. There's an RSS feed on our website. I still haven't looked to see if we're in Stitcher. I probably should do that.
I was just going to ask.
But you can get our RSS feed. I'm pretty sure that you can subscribe to an RSS feed in Stitcher, and you can find that at our website, emmunity.org. You can also find us on Facebook. You can leave us comments on Facebook or on our website, or send an email to comments@emmunity.org. And thank you, Matt Woodruff and Kate Franz. I'm Kevin Bonham. Oh, I should say the music at the beginning and the end of the show is composed by Rachel Reineck. And we'll see you next time.